Welcome back to DataMindAI Snowflake Architecture Series. I am Ahmed Mahmoud, Principal Data and AI Engineer. In the last episode, we explored Snowflake's storage layer, how data is organized, optimized, and made incredibly efficient. Today, we move up one level in the architecture to the heart of Snowflake performance, the virtual warehouse layer. This is where compute happens, where queries run, transformation execute, and workloads scale independently without impacting each other. In this episode, we'll break down how warehouse work, why they are radically different from compute in traditional platform, how scaling behaves in practice, and how to choose the right warehouse strategy for your workload. And in the next episode, we'll complete the architecture by exploring Snowflake Cloud Service Layer. For now, let us unlock the power of Snowflake's compute engine. Now, let us talk about compute, the virtual warehouse. Before we dive deep into Snowflake warehouses, here is the simplest way to think about them. If storage is where your data lives, then the warehouse is the engine that brings that data to life. Every query you run, every dashboard you refresh, every pipeline you execute, it all runs through a warehouse. And what makes Snowflake special is that this engine can instantly scale, isolate workloads, and never slow down other teams. So today, we are opening up the hood and looking at how this engine actually works. This is how Snowflake actually processes your queries. So what exactly is a virtual warehouse? Think of it as an independent cluster of compute resources, essentially an MPP or massively parallel processing cluster. Each virtual warehouse executes queries completely independently without sharing resources with other warehouses. Here's why this matters: elastic scaling. You can scale a virtual warehouse up or down instantly. Need more power? Resize from small to X large in seconds. The transition is seamless. Multi-cluster warehouses. When you have high concurrency, many users running queries simultaneously, Snowflake can automatically add additional cluster to handle the load. This auto-scaling prevents queuing and maintain performance. Auto-suspend and resume. When a warehouse isn't being used, it automatically suspends and you stop paying for compute. When a query comes in, it resumes instantly. This is crucial for cost optimization. You only pay for compute when you are actively using it. Workload isolation. You can create separate virtual warehouses for different teams or workloads. Your ETL process runs on one warehouse. Your data science team uses another one, and business intelligence runs on a third. They never interfere with each other. So this compute layer design means your query performance is predictable, isolated, and cost optimized. You have complete control over the compute resources dedicated to each workload. In Snowflake, all compute power is delivered through something called a virtual warehouse. Think of a virtual warehouse as a cluster of compute resources, such as CPU, memory, and disk, that Snowflake allocate to run your workload. So different sizes for different needs. On the left, you can see different warehouse sizes represented as gears: S small, M medium, L large, and XL extra large. Each size represents a different amount of compute power. As you scale up from small to medium to large, the compute resource doubles each time. This means more CPU, more memory, more parallel processing, and ultimately faster execution for heavy workloads. What runs on a virtual warehouse? So any job that requires compute, whether it is loading data, transforming data, or running queries, uses a virtual warehouse. Snowflake separates compute from storage, as we said before, so scaling your warehouse size has no impact on how your data is stored. Credit consumption. While a warehouse is running, it consumes Snowflake credits. You are charged only when the warehouse is active, and Snowflake automatically suspends it when it is idle. This gives you full control over cost. Turn the warehouse on when you need power, turn it off when you don't. So in a nutshell, so in Snowflake, virtual warehouses are elastic compute clusters that scale instantly, power your queries, and only bill you while they are running. They are one of the key reasons Snowflake workloads are fast, flexible, and cost efficient. Snowflake use workload segmentation to keep different types of jobs isolated, predictable, and highly performant. Why workload segmentation matters? So in Snowflake, the different workloads have very different compute requirements. If all workloads share the same virtual warehouse, heavy jobs can slow down lightweight ones. To avoid this, Snowflake lets us run each workload on its own dedicated warehouse. Now, the prod database as a shared source. At the center, we have the production database. All workloads read from the same centralized data, but they run on a separate compute cluster, ensuring workload isolation. So the data science, large compute needs. On the left, we have data science workloads running on 2 Excel warehouse. These jobs are typically CPU heavy, involving machine learning, feature engineering, or statistical modeling. So they need large scale compute power. Interactive dashboards, many small warehouses. Next, we have interactive dashboards powered by 5 small warehouses. This setup provides concurrency. Many users can refresh dashboards and run queries simultaneously without competing for resources. And now data transformation, medium warehouse. In the middle, data transformation jobs run on a medium warehouse. These are your ETL and ELT transformation, processing moderate volume of data, usually on a schedule. And then you have ELT or light jobs, X small warehouse. On the right, we have ELT tasks running on X small warehouse. These are lightweight operations such as incremental loads, metadata updates, or quick data checks. So an XMOR is perfectly sufficient. So the result, no contention, predictable performance. By isolating workloads by size and purpose, Snowflake prevents resource contention. Dashboards stay fast, data science jobs run efficiently, transformations stay predictable, and small tasks don't get drowned out by bigger ones. In a nutshell, workload segmentation ensures that every workload gets the exact compute power it needs, no more, no less, while maintaining performance, isolation, and cost efficiency. In Snowflake, you can choose between 2 types of virtual warehouses depending on your workload requirements, the standard warehouse and the multi-cluster warehouse. The standard warehouse. On the left, we have the standard virtual warehouse. A standard warehouse is always a single compute cluster. If you need more compute power, you scale up to a larger warehouse size, like small, medium, or extra large. And Snowflake gives you more CPU and memory inside that one cluster. This option works best for predictable workloads with moderate concurrency, where you don't have many users or queries hitting the system at the same time. Multi-cluster warehouse. On the right, we have the multi-cluster warehouse, or MCW. Unlike a standard warehouse, a multi-cluster warehouse can run multiple clusters at once. Snowflake automatically adds or removes clusters based on demand. If concurrency goes up, for example, many users running queries at the same time, Snowflake brings additional cluster online. If demand drops, Snowflake scales them back down to save credit. This elastic scaling makes multi-cluster warehouse ideal for high concurrency environments such as BI dashboards, shared analytics, or peak time reporting. Availability. Multi-cluster warehouse are on the enterprise edition feature, so you need the right subscription tier to access this level of scaling. So in summary, standard warehouses use a single cluster and scale up. Multi-cluster warehouses uses multiple clusters and scale out automatically. Choosing the right one depends on whether you need more raw power or more concurrency. Now, let us break down one of the most important concepts in Snowflake performance tuning, the difference between scaling up and scaling out, and how that translates into credit per hour. On the left-hand side of the chart, we have the virtual warehouse sizes, ranging from X small at the bottom to 4 extra large at the top. As you move upwards, each size doubles the compute resources, that is CPU, memory, and I/O. Across the top, we have another dimension, the number of clusters. This is what Snowflake uses when you enable multi-cluster mode, typically for concurrency. Now, notice how the numbers inside the matrix increase both vertically and horizontally. Moving upwards means scaling up, choosing a larger warehouse for more power. Moving to the right means scaling out, adding more clusters to handle additional users or simultaneous queries. Let us look at two highlighted examples. On the left, we see X large, which is one cluster, but 16 credit per hour. This represents scaling up. We choose a bigger warehouse to process a heavier workload or a more complex transformation. On the right, we see medium, but 4 clusters. Before, it was only one cluster, but now we are choosing a medium, but 4 clusters. But the 4 clusters also, they cost you like 16 credit per hour. Here, instead of increasing warehouse size, we add more clusters. This scaling out for concurrency, ideal when you have many dashboards, analysis, or power jobs that need to run without waiting. Both configuration cost the exact same 16 credit per hour, but they solve different problems. Scaling up for query complexity, scaling out for concurrency. This is what makes Snowflake so flexible. You can tailor performance to workload without overspending.